So this is the second class of Fourier series. So in this class, the topic I am going to cover, obviously the first class, I have given some introduction about the Fourier series, what it is. Now, a Fourier series, in the previous class, as I mentioned, that Fourier series can be expanded in, if fx is a periodic function, then fx can be expanded as a0 by 2 plus sum over a equal to 1 to infinity an of nx plus bn sin nx, where this a0, an and bn are coefficient you have to determine, right? So for different Fourier function, for different value form of fx, this Fourier series become different. Okay. Now, as there is a function of sine and cosine function, you can express this series. So you see that this, as this is a complex, so this is ultimately a sine and cosine function. So it can be expanded in the complex form. So I have to take the complex form of the Fourier series. Now, as you see that cos nx to the power ix is equal to cos x plus I sin x, and to the power minus ix is equal to cos x minus I sin x. Right? So if this 2 is true, then for cos I in x, this must be equal to, obviously this should be cos in x and I sin nx, and this, if this is I in x, this should be cos nx and I sin nx, right? So cos function is basically, I can write cos nx equal to half of e to the power I nx plus e to the power minus I nx, and sin nx on the other side can be written as 1 by twice I e to the power I nx minus e to the power minus nx, right? So these two terms can be replaced in the Fourier expansion, in the Fourier series expansion, to get the complex form. Now, what is the form of that particular Fourier series in complex term? So fx can be given as a0 divided by 2 plus sum over n equal to 1 to infinity an of nx plus bn sin x. to replace this cos nx and sin nx in terms of e to the power I nx plus e to the power minus I nx. So the Fourier series becomes a0 by 2 plus sum over a equal to 1 to infinity. Here, in place of, I can write an into half e to the power I nx plus e to the power minus I nx plus bn half e to the power I nx minus e to the power minus I nx. Right? Now we have to replace the whole thing in a simple manner so that you can replace this bn and n in terms of some specific coordinates in terms of e to the power I nx and e to the power minus I nx. So I can write the simple form as a0 by 2 plus sum over a equal to 1 to infinity. This should be half of an plus here must be twice I. So 1 by 2. So this should be bn divided by I into e to the power of nx plus half an plus this should be minus bn 1 I e to the power minus I nx. Right? So I can replace the whole thing in this pattern. Now, what you do here, we just move this I to the numerator. So here the term minus IBN and this will be plus IBN and the rest remains as it is. So if you change the whole thing in this way, you can write that fx in terms of sum of n equal to 1 to infinity, rather I can say n equal to 0 to infinity. I put this constant term into here where Cn to the power I n x obviously. Okay, so and if you put this plus sign plus Cn prime to the power minus I nx. Okay, and this should be sum over n equal to 1 to. Now if you choose combine both of them together and put a constant factor here, you can change fx as sum of n equal to minus infinity to plus infinity. Just combine these two forms in a simple way in one term. Cn to the power I nx. So minus infinity means this term and plus infinity means this term in between two n equal to 0 with this constant. Right? So I get the complex form of this equation. Now as this is a complex form, you have to derive this coefficient using this complex form. Now what are the coefficients? How could you get this coefficient from the complex term? Now let us consider the Fourier series in this form and this is a bound function in between the bound limit minus 5 to plus 5. Now if minus 5 plus 5 becomes the bound limit, then what you do here, you just integrate this function fx from minus infinity to plus infinity with respect to x. Now if you integrate the whole thing by multiplying sum e to the power I in x, where a is the dummy index. So you have to integrate minus infinity to plus infinity if x e to the power minus I in x times dx. So what you will get at the right hand side, you get that sum over n equal to minus infinity to plus infinity, integration minus infinity to plus infinity, c n e to the power I in x e to the power minus I in x dx. Okay, this cn term contains both a0, an and b term. Now what you will get? You get that, so remove this sum here to calculate the integration. Okay, so if you remove this sum, what you will get? You minus infinity to plus infinity. C is a constant, so bring it out. So e to the power I n minus n x into dx. Now what is the value of this e to the power I n minus n x into dx? We know that this function becomes a delta function as is an exponential function. So when this e to the power I n equal to n, then the function gives the maximum value, and otherwise it becomes 0. So if you just integrate this term, what you will get? You get cn twice pi. Okay, so as this is cn delta mn, so this becomes cn. So you will get cn times twice pi. Now what is the value of this cn? So cn or cn, which I get here, or which I assume here as a coefficient, the value of this cn will be, or cn, and that cn here. So this will be 1 upon twice pi integration minus infinity to plus infinity fx to the power I in x. So in this way you can calculate the coefficient of a Fourier series in complex form. So first we can change the Fourier series into complex form, and then you can calculate the value of this coefficient assuming this fx in constant complex form. Now we can find the Fourier series in the interval of twice pi, where I choose my convenient interval at minus pi to plus pi. Now the situation is not always same, because you never get this bound region for all types of function. So now assume that the function is well defined function, and the function is bounded in some other region between L minus L to plus L. Okay, this function is not minus pi to plus pi, but it becomes minus L to plus L. This is the bound region of a function x. Right? Now you have to expand this function in Fourier series. Now what you will do? You can assume here that the total period of this bound region is twice pi, and in similar way the total period of this bound region is twice L. Right? So, as total period of this bound region is 2 pi and this bound region is 2L, you have to change this bound region into the form of this bound region in terms of variable x. Okay, so this is the independent variable. This variable moves from minus pi to plus pi. In a similar case, you have to change this variable function from pi to L. So what you will do now? You choose the twice L interval, given that twice L interval is defined for function x. Now, the same period, if this is 1 unit period, what is the value of this function? This is just this function is scaled by x by twice L. Now you have to change this twice L period to twice pi. So if this is twice pi period, this will be x by twice L into twice pi. So this will be pi x by L. Now assuming this as a new variable z, where you just scale this independent variable x with a constant pi divided by L. Okay, so you just scale it with a constant pi by L. So this pi by L is the scale factor. Okay, so we just use the scale factor and we will have changed this variable to z. Now this function fx becomes f. In place of x, you have to write Lz by pi. So as pi x by L equal to z, so z x will be Lz divided by pi. So the function will be zl divided by pi. Okay, and you just say this is capital Fz function. So you have to take the Fourier series of this capital Fz function. Now if this is capital Fz function, this is a similar function like x, only I have used a scaling factor L by twice pi, nothing else. Okay, so what you do here, as you choose some scale factor here, so the Fourier series must be f z equal to f by x by L, and the value of this Fourier series will be, or I can write here as fz, so you can write here Lz by pi. Okay, so I can use the similar form of the Fourier series as a0 by 2 plus sum of n equal to 1 to infinity an cos z nz. Now the new function is as it is z, so this is nz plus bn sin nz. Right? So I have just used this z function in terms of x to expand this Fourier series. Now what is the value of this a0? Now a0 will be what I will get from my first term, that is 1 upon pi, and you change this z from minus pi to plus pi. So the value of integration change from as this is as this interval of twice L, so I can use vector minus pi to plus pi z times this, right? So if this is fz times dz, so this will be nothing but 1 upon pi minus pi to pi f L z by pi. The z is replaced by Lz by pi into dz. So what you will get from here, this will be 1 upon pi. Now you change this term from z to x, so this will be minus L to plus L if x d of pi x divided by. Okay, so bring this pi by L as it is constant outside. What you will get 1 upon L minus L to plus L x. So the value of A0 is 1 upon L minus L to plus L x. Right. Now, what is the value of this An? Now, in the similar way, An will be 1 by pi minus pi to plus pi if z cos nz is. Okay. So xz cos nz is. Now we have to replace the whole thing to from pi to L. So what will you get? This is 1 upon pi minus L to plus L. You have to change this function. So this will be f of pi x by L cos n pi x by L. This should be d times pi plus pi. Okay, so again you just bring this pi by L outside integration, and what you will get is 1 upon L minus L to plus L if x okay n by x by L d times d. So sorry, here you will write pi Lz by pi, as this is L times. Okay, so to change the complex function or to change the scale from pi to L in this way. Now the value of Bn in similar way, it becomes 1 upon L minus L to plus L sine n pi x by l dx. So this is the way that how could you change this whole function from twice pi limit to twice the limit. Right? Now take an example of a half-wave rectifier. So what is a rectifier circuit? If you give the input in a sine form, as this is half-wave rectifier, so output will be just the positive part of this function. Okay, so you will get only the positive portion. You never get this negative portion at all. So this is the form of a half-wave rectifier. Now, this rectifier, if you run it between the interval 0 to twice pi, so this is 0, this is pi, this is twice pi. So what we will get from 0 to pi, this rectifier has a specific form. Okay, and output have a specific form. And when it will go from pi to twice pi, the form of this function becomes 0. So there is some discontinuity, but this there is finite number of discontinuity between the bound limit 0 to twice pi. So you bound limit is 0 to twice pi. And in between the 0 to twice pi, there is finite number of discontinuity. Okay. So if x will be sine x between 0 x to pi, and f x becomes 0 when you get this two limit. Right? So this is sine x and this is 0. Now what is the value of a0? So a0 will be 1 upon pi, as this is 0 to twice pi limit. So fx dx, so 1 upon pi, we have to take integration 0 to pi, where this function have sine x form, and otherwise this function from pi to twice pi, this function has 0 x. Right? So this becomes 0. Now what is the value of integration sine x into dx? Integration sine x into dx, this will be 2. So this becomes 2 by pi. So a0 will be 2 by pi. Now, what is the value of this an? The value of this an is 1 upon pi integration 0 to twice pi if x cos in x into dx. Now this will be 1 upon pi 0 to twice pi, put fx as sine x, or if you put 0 to pi limit, you will get sine x cos in x into dx plus other part from 0 to twice pi, this bound limit from pi to twice pi. Okay, so this becomes 0. Now, if you integrate this part, what you will get? You will get that when n is even, then this sin x dot cos x, I can expand this in terms of sine series. So this becomes sin n plus 1 x plus sin 1 minus, sorry, this is wrong description, minus sin n minus 1x and to the half. Okay, so when n is even, then this n minus 1 or n plus 1 becomes odd. So when n is even, this n plus 1 return the factor minus 1 for cos nx, right? So which in turn give us a result minus twice 2 divided by pi times 1 upon n squared minus 1 when n is even. But when n is odd, so this, if n is even, then n minus 1 or n plus 1 both becomes odd. Okay? But when n is odd, then n minus 1 or n plus 1 both becomes even. So this integration of sine function becomes cos function. So if you put pi or 0 here, it returns always plus 1. Okay, so the value of the integration becomes plus 1 always. So what we will get from this, that when sine function returns to a cos function with 2n pi period, so what we will get? So cos 2n pi here. So if n becomes even or odd, okay, so n becomes either this is 2n pi or cos 0. So value of this cos 2n pi is always plus 1. Okay, so as the value of this 2n pi is plus 1, then this term always give me 0. So for n equal to even, this gives me this, n equal to odd, this is 0. So an is a specific form, and I can write an as zero for n equal to odd, minus 2 by pi 1 upon n squared minus 1 when n is 1. Okay. Now calculate Bn. So Bn equal to 1 upon pi 0 to twice pi fx sin nx times dx. So this value of this fx from 0 to pi, this becomes sin x, and from and the rest part, my pi to twice pi, it becomes 0. So this will be 1 upon pi 0 to pi sin x sin nx. Okay, plus another term 0 for pi this bit. Now, what is the value of this sin x sin nx dx? Now, if you choose sin x sin nx dx for n equal to 1, this function gives me a specific value. What is that? That is basically half. Previously I have done this. So this is sin x, so this is sin square x, so half of 1 minus cos x function, and 1 minus cos x into pi here, so pi divided by 2 into 1 by pi. So that gives me just half, right? But this gives me 0 for all n values except n equal to 1. Okay, so just B1 term that exists for n equal to 1, that is only B1 term exists, and the value of B1 is just half. So if you expand this half wave function in terms of Fourier series, if we will get that f is, so let us first write the Fourier series function a0 by 2 plus sum of n equal to 1 to infinity an of nx plus bn sin nx, and this a0 here 2 by pi, so this will be 1 upon pi for half wave series, half wave rectifier. Okay, so 1 upon pi plus, for n equal to odd, this becomes 0. So we have to write the Fourier series in such a way that this becomes minus 2 divided by pi 1 upon n square minus 1, and obviously sum here 2 by pi, sum here n is even only. So this becomes 1 upon n square minus 1 cos nx, so n is even, plus half sin n becomes 1, so half sin x. So this is the ultimate Fourier expansion of a half-wave rectifier. So now I get this thing, and next class I will continue with some other part of this process.